Okay, I'm going to take a look at problem 4.13, and this is a problem where you have a 160 kilogram crate hanging from the ceiling, and you're looking for tensions in two ropes, AB and AC. Okay. Now, what we can see right when we start off is that we have two unknowns. Okay, we don't know the tension in either of these cables, either in AC or in AB. Okay. So that tells us that we need to have at least two equations, two independent equations for this, all right? Okay, so the first part of this solution, what we can do is we can actually draw a free body diagram, okay? And with the free body diagram, usually you're isolating basically part of the system. If we think about it, if we look at it from the perspective of point A here, and with a free body diagram, we would draw forces off of this point. We have a force going down in this cable, we have one going up here, and one going up in this direction. Okay. All right, so here's our free body diagram for this problem. All right. So in this case, what you're starting off with three forces. And W, we can solve for that very easily because we're given the mass of the crate, which is 160 kilograms. So if we multiply that times 9.81, we can actually come up with the weight in newtons. All right, so if we do that, the weight of the crate is just 1570 newtons. Okay. Now the next thing we need to do is we need to come up with equations that are, so we know the force, we already know the force in this one, right? This is the cable here. This is already given as the weight going down. We need to come up with equations, two equations, one in the along the x-axis, and one equation along the y-axis. Okay. So first in the x-axis, if we think about the components or the forces, the components of the forces, this for potentially, or this tension, and weight in the x direction, what we would see is that since the weight is going straight up and down, or straight down, that's along the y-axis. So there's actually no component in the x direction. All right. So what we're going to see is we're going to have some component in the x direction, sort of pulling off in this direction, and another component of a component of TAC in the other direction, pulling off to the right. Okay. So if you think about it, in an equilibrium condition like this, where it's not moving, there's no acceleration, right? Is that however force you're pulling off to the left has got to be equal to whatever force is pulling off to the right, okay? Otherwise, this thing would move off in one of these directions, right? So basically, we were just going to say is that tension off to the left in this direction is equal to the tension off to the right, okay? Or the x component. So we could say TABX is equal to TACX, or the x component of TAC and the x component of TAB. Okay, so those have to be equal. All right. So the first part of this is, we can actually have some assumptions here. So all forces concurrent at point A, meaning they all basically meet at point A. The weight, so the ropes are negligible. Well, okay, this problem they didn't give you anything about that. And the ropes are taut, or they're tight, right? They're pulling. All right. So some of the equations, we have the weight is equal to mass times gravitational acceleration. And then for static equilibrium, meaning essentially there's no acceleration, or in this case even no motion, we'd say that all the forces acting in the x direction are equal to 0, and all the forces acting in the y direction are equal to 0. Okay, so those are our two equations. These are equations for equilibrium. Right. So the first part is, of course, the crate, its weight, and then the equations. Okay. So what we're looking for, if we think about it like in this case, we're looking for the tension off in the x direction. Right. So we can use the trig functions for that, and they're actually going to be the cosine function. So if we go back up and we look at the angles here, we're looking for this part of the force, or the x component of the force. Okay. And the x component of this force, right? So to get the side, if you think about this as being like a right triangle, to get the x side, it would just be the cosine of this angle times the overall magnitude, or the hypotenuse, right, which is just the magnitude of the force or the tension. The same thing over here. Now it's going to be cosine of 70 times the magnitude TAC. Okay? And that's all this is here for the equation. Okay. So the next thing is that you create an equation for the y components. Now in this case, you have the weight also, and you're trying to find, with right triangles, you're finding the component that's basically the vertical component here. And if you want to think about it, we could think about drawing it straight down. Think about this tension as a right triangle. Okay, represented that way. And same thing over here. So we're looking for the actual side opposite the angle. So that's going to be the magnitude times the sine of the angles, each of the angles. All right, so in this case, of course, it's magnitude times sine of 35. All right. So in terms of the directions, right, if you think about it like we're thinking about a standard Cartesian coordinate system, so off to the right is positive, off to the left is negative, okay? And that's all that's written here. It's just TAC cosine of 70, which is off to the right, and minus TAB cosine of 35, which is to the left, okay? Now, in this case, the same idea is that the positive y components are TAC sine of 70 and TAB sine of 35, and then minus W, right? Okay. So in this case, there's actually kind of a step here that's missing, and what I'll do is I'll do that by hand to show you that. Okay, so continuing on with this problem. So if you make the substitution into the second equation, solve for the unknowns, you can come up with an answer of 556 newtons, okay? So let me just go through the steps here. So basic idea, at least the approach I took, was I solved for TAC in terms of TAB. So I started with the equilibrium equation in the x direction and just wrote it out, and then I wrote out, I took and put TAB on one side, TAC on the other, and then I divided the right hand side, both sides, by cosine of 70 degrees, and when I did that and I substitute in, I have TAB times 2.4, okay? Now I took that equation, or TAC in terms of TAB, so I just substituted in for TAC with this, TAB times 2.4, okay, into the summation of the forces in the y direction, which is just this equation here, okay? And when I do that, and I solve 2.4 times sine of 70 degrees, I come up with 2.25, and then when I solve for TAB sine of 35 degrees, comes up to be 0.57, this is 7.4, okay? And then I substitute in for W, right? So when I do that, I just put 1570 newtons on the right hand side of the equation, combine these two, and then divide both sides by the sum of these two, which is 2.83, and then I come up with 556 newtons for this problem, okay? So this was like the missing details that the solution set didn't have. And that is basically it for this particular problem.